there is a poll. Start with it. Okay, so as per the poll results, if you can see here, um, most of the people, some of the people in Zeocore already know about the free monads. I'm assuming Connect hasn't gone through the data expectation code base. So I'll be covering some of the free monads again. So if you are, kind of not interested in the free monads, you feel free to drop off. We are again covering free monads from the point of view of data IO. So if you want to, go over that, feel free to stay back. Okay. Uh, yeah, let's start then. You can also join back later, maybe check back in half an hour or so when we are in the halfway mark, and then you can continue from there. Okay, so basically we have written a module called Data IO. It's still in a pull request phase, but more or less the pull request is done and it will be merged within this week. So you guys can start using this library. And the idea is to show the usage and what is internally involved there, okay, to make better sense. So that you can also start contributing to the library. That's also another very important point here. So let's move on. Okay, so what was the problem statement that we were trying to solve in say as a player? I don't know. I have raised the poll. I think you'll have to go to the poll section, probably, Satish. Okay, so I'll start with the problem statement that we were trying to solve. So you must have seen in Geotab, I'm specifically taking the context of Spark because that's what all of us mostly write code in, although Connect team also works on Kafka and ScyllaDB. So the problem statement, uh, okay, yeah, then it doesn't apply to you. Okay, so the Connect team is, or say the Zeocore team, we do a lot of these source loading and sync writing, right? And we've written a lot of this code, spark.read. Something, and then when you get the data frame, you try to do all sorts of, say, magic to it. Say, suppose you want some kind of an optional column. Okay, so what that means is, if the column is present, take that column. Otherwise, just take a, say, suppose a placeholder, say null value is a placeholder column, okay, which if it is present in the original data frame or original data, keep it. Otherwise, just put a placeholder column. Then there is a feature called look back, which we use in pre-process, which is basically you look back the last 7 days in terms of the path, and then you just pick whichever is available. Like that, there are many and many features which we keep building out in different repos, but none of us can reuse those features because of the fact that it is built out first of all in different repos, and then probably the structure is also not very conducive for usage, for use basically. So our first idea was to not only write a source loading or sync writing library, because there are many umpteen number of libraries. You go to Akka, you go to any such flow-based libraries, you'll find the concept of a source and a sync. So our idea was to write it in a reusable fashion. So if you just concentrate on the keywords there, you'll just see that that was the idea. And second idea was not to couple it to a platform. When you look, so at a high level, at a business language level, nobody is worried about, or maybe the product team is not really bothered about the fact that whether we are using Kafka or Spark or Beam or whatever to load the data, right? To load the data and do operations on it. All they are worried about are the operations, the business language, right? So we want to segregate, give a business language to the user. Okay, right now maybe the consumer of this library is not directly product, but then you do the discussion with product, and then there should be a high level way of interacting with this language where we just talk in business language, and the implementation can later be directed to a platform, say Spark or Beam or Kafka. something like that. Okay. So this being the problem statement is where we started. And so first we'll see what are the goals for this platform. So the goal, number one goal is standardized data reading and writing. Obviously, that's why the name Data IO. Second is build a standard set of reusable features. The features which we are writing should be reusable code. Okay, anybody can, use that. Anybody can contribute to that. Some other team. So reusable has many contexts here. One team writing, the other team reusing. One team writing, say suppose the construct, say suppose the language itself is reusable. When we talk about a domain specific language, the language itself should be reusable for different platforms. We don't need to, so you can load data, say suppose in Bigtable like an Avro, and you can load data in Spark like an Avro. Keeping the business language same really helps, because tomorrow you can write separate platforms, direct the same language or business language to load to work for a platform like Spark or BigQuery, right? So that was one of the goals. Third thing is develop a domain specific language. Now, a domain specific language is very useful, okay? In terms of whenever you want to build a business language, you always look at a DSL, okay? So say suppose a very widely known, commonly used business language is SQL, right? Business users, the BI users, product, data science, data engineering, normal software engineers, everybody talk the language of SQL. And when you say select star from so-and-so table, order by this, everybody has the same visual representation in their head. That's the key point here. Everybody should think about the same visual representation. Later, that SQL is taken and maybe targeted to a Postgre platform, maybe targeted to a MySQL platform, maybe targeted to a Spark platform, doesn't matter. When product is talking about a SQL, they have a visual structure of it. And that's how you would want your DSL to also be built, right? So a common language which very much embodies a DSL, and then we can build upon that. You can code using that common language, okay? Another goal, so I'll move on to the next goal. Next goal is segregation of domain and platform, which we have already talked about. Design philosophy wise, we wanted to keep few things very importantly. Maintenance should be easy. So we'll tell you the woes that we faced. So we have written some piece of code, and next time when people start writing code to it, there is no clear-cut philosophy there. So they don't know where to put what set of code, right? And then that is where the mix-up happens. That is because of this, lack of philosophy. What happens is generally the domain and platform tends to get mixed. And that's where the problem lies. If you have a clear philosophy, you know where to put the domain wala code. You know where to put the platform related code. You know, within the platform related code, where what goes in it. Everything has a defined place in the code base. So there is no way, even if there is a bug that you have written, it is very easy to isolate that bug. It is very easy to debug, because there can be only one place where it must have gone wrong, because everything is so well defined. So that's one of the things that we wanted to do. Second thing is, again, new code addition should be isolated. What I spoke about, that it should be isolated. And when somebody is adding a new code, entire piece need not be tested. Only that can be unit tested or property tested. And that feature, we can confidently say that addition of this new feature will not break the old code, because it has been written in such a way. Okay. And finally, easy to use. The facade, the external API should be very easy to use, so that person who doesn't really care about the design philosophy and stuff like that, which is working internally to augment the code, can also use it very easily. Okay. So those were our design philosophies. Okay. So let's move on quickly. So first, I just like to go back. This is, I think I have spoken about this stuff earlier also, but just for the Connect guys and for our interns who have just joined. So I'll just repeat that. Okay. So first, I'd like to talk about few terms and then go back to connect it back to our code. Okay. So first, the concept of reification. So what is reification? Okay. So I know I have made this point a lot of times, so a lot of you might be laughing, because I have spoken about this a lot of times, right? But yeah, I'll reiterate myself. So reification is the process of making something which was abstract, making it concrete. Something which was abstract in your code, you make that concrete now. So an example, so the process is basically take some concept, that is implicit in the code, turn it into data, which can then be manipulated by the program. Okay, that's a simple concept. Okay, something which was implicit in the code, turn it into data, and then that can be manipulated by the program. Okay, so let's see an example here. What I mean by this. Okay, functional. So the first very pertinent example is functional programming itself is a concept of reification. Okay, so in OOPS, functions are not data. You cannot pass around functions. Okay, maybe in the later versions, but the original OOPS you cannot pass around functions in Java, right? But that is possible. So functions also act like data in functional programming, right? So maybe you can think of the instance of Scala where you can pass around functions because functions are also data. Okay. Second concept, second example is option. We have all used option, and that's a um, very naive concept of partiality. Either the result will be present or it will not be present, some or none. Now you see, you took that. So we might be very naively passing around these options and working with them. What you're passing around is the concept of partiality. The person or the function returning an option, somebody else who is working with that option, he's basically working with the concept of partiality. He knows for a fact that this value might or might not be present, some or none, right? So you're passing around concepts. So you're taking something which was abstract in your code. Earlier, what would we do in a Java world? We returned a null, right? What does that null embody? It embodies that when you don't know what to do, you've evaluated a lot of things, and now you don't know what to return, and you returned a null, right? And that null, people guarded against that null. But that was all abstract in the code. It was all implicit in the code. Everybody was handling their nulls very with ease, and nobody was really talking about this concept of partiality. So what option does is takes this partiality and gives it to you so that you can work with that. Okay, so that is a reification right there. Okay, more examples everywhere, basically. Okay, so in Akka streams, you have flow, which is the reification of the concept of processing stages. So you have processing stages, which is reified like the different flows that you have. And within that, you'll have those fork and joins. The data is totally separate from it, but the concept is reified in a flow. Okay, so Kleisli is something which reifies the concept of effectful composition. Okay, so we'll not get into this right now because there is a video for this on our knowledge transfer page. Okay, trampoline is again a very good data structure to talk about here because it's easy to explain. So your stack safety, right? Stack safety was always implicit in Java. Okay, now you take that stack safety, put it in a data structure called trampoline, and you can pass it around now. So you are actually coding with stack safety. That was an implicit knowledge, and something which was abstract was taken, reified, and given to you. Now you can code around that. Okay, and then all of these generally may or may not be monads. So you will have all the standard properties being applied to them, monads or applicatives. Okay, DSL. Another example of reification is a DSL itself. Okay, so in the sense that when you are writing a DSL, don't you think? So we'll come to that. How is it a reification of a concept? Let's see in practice probably. Okay, so this is a DSL. So what is a DSL? I'll just go into that first. Already spoken about it. It's a business language like SQL. You can that can be your visual representation right now in your head. It's like a business language which people talk about. So in case of data expectation, why I took that poll is in case of data expectation, the business language was product is not really bothered about you do the verification of data using Spark or using BigQuery or whatever. They were just talking about data, right? Whether this column or whether this data is null or not, whether this data is string or not, whether the age is within 25 to 35 or not, whether the gender is male or female or not, right? This is what their business language was. So we wrote something which is around that business language that, hey, you have an expectation, which is like should be string, should be Boolean, or one of these values should be male or female. So one of these values or within valid age range, okay? The accepted geotab bucket basically. So that was the business language that we were trying to talk about, okay? So again, has an inherent meaning pertaining to business. Now, one point to notice here is it talks about what and it forgets about the how. What I mean is the product really talks about the actual data, what it is, and what are the expectations on that data. It never ever talks about how you will do it, right? How means the implementation, whether it's Spark, whether it's BigQuery, not required. There is a language, everybody talks in that common language. Even for SQL, everybody is talking about the select star from table. Nobody is bothered about whether it will run on Postgre or MySQL, right? Everybody is talking in that common language, forgetting about which server it is running on. Okay. So again, not bothered with the implementation. Okay. So this is the basic of the DSL part. I think you've already got that. So now let's look at how to do this. Okay. So here I would just like to toggle 1 second, guys. To our basic data expectation, the first module. I've kept the modules kind of same to make it more apparent. Okay, I'll share this tab. Same kind of same presentation. Yeah. So let's look at this. So like I was saying, there's something is should be present. So I'm just showing why I'm showing this is easier to explain first, and then I'll move to the data IO part. So how would you have written something which was implicit in the code? Look at this. If you would have written, say, suppose you're checking whether a column is present or not in a data set, there would be a method. Okay. The method would probably take some column here. Okay. So this is a method that you've written. Definition should be present, doesn't take anything. That's why I've written unit. It just directly knows which column to check, or maybe it can take a column name also, and it returns you a Boolean, true or false. This being a method, okay, is implicit in the code. You can call this, but when you take this, make it a, say, case class or a case object, which is basically you're turning this into a data, okay, that is the reification there. How we'll use the reification will come to next. But the idea is this is a reification there. I took this thing, somehow it was a function, I converted it into a case class. I still don't know what to do with it, but just believe me for now that I've taken this data, taken this function, converted into a direct case class, should be present. So it doesn't take anything, so nothing to, it's a case object. And then there is an interface, looks like it extends some interface called data expectation. And then there is a Boolean. Now notice one uncanny similarity, that it exactly embodies the method signature. Okay, the should be present. So the should be present here is has very much similarity to this method. It doesn't take anything. This method didn't take anything. And whatever you are returning is somehow now part of the generic type which this interface takes. Okay, very much, represents the entire method, but looks like a different representation. Let's explore what this different representation is. Okay, so having said this, let's move on. So now see, we are defining a DSL. Okay, how to define this DSL that we have been talking about so much. Okay, so there is, okay, one thing is, any questions till now, guys? Anything that is not probably flowing logically or not making sense? Okay, I'll assume there are no questions. I'll move on. So, okay. So if you see here, we defined a trait, which is an interface. Sealed trait. Why sealed trait? It may or may not be sealed trait, but sealed trait because when you're going to implement these case objects, or we're going to give implementation, then it throws you a compiler exception. That's it. Otherwise, also sealed trait because it cannot be extended, because the idea is whatever expectation you write should not be extensible outside and somebody else starts changing those expectations. So that's why it's sealed trait, so that nobody can extend it. And then this is the interface data expectation, and it kind of returns, it kind of gives, takes a A. Okay. So here what we are saying now, I'll just talk in terms of plain English and you'd see if it makes sense. Okay. So this expectation is extended by this case object, which is called should be present. And somehow it evaluates this and returns you a Boolean. whether it is present or not. That's the Boolean. So this is an expectation at a high level. This is a data expectation, and this guy will return you a true or a false, whether the expectation is passed or failed. This is an expectation. What is the expectation? Whatever data has come to me, it should have one of these entries. Say suppose for a gender, it can be male and female, nothing else, others, nothing else should come there. Okay. So one of these entries should only be held in the data. Notice that we are not talking about what kind of data, where it is residing, nothing. We're just talking about the business rules. Okay. So one of these values should be present, and this guy after that will return me whether it passed or failed. This rule, this data expectation, passed or failed. Okay. So this is a simplified version. Our current data structure is a little more complex, but this is a simplified version of the data expectation framework. Same goes for non-null always. Say suppose it's a country column. We all know that country column has to be non-null, right? So then you do that and you directly, it gives you whether this expectation passed or not. Okay. So this is the first writing the DSL part. Think of this as you're writing a node in your language. Okay. So one parallel example that I would like to give is, I was just checking this thing out. So if you look at this, okay, this is a AST Explorer. Okay, so any language you go into, okay, you write a code, right? That first gets transformed into an abstract syntax tree, right? Into some kind of tree structure, right? How would you, so what are the basic constructs of SQL? The basic constructs of SQL are select, from, I'm just talking about SQL because that probably makes the most sense. Select, from, where, order by, right? So if you go to this website, astexplorer.net, you'll get all sorts of ASTs that you can write some code and you'll see the corresponding AST. If I choose Scala here, see how the AST changes for that. Okay, how your main and your println and everything is represented this is the AST of a compiler, basically how you can store your language, okay, in the form of a tree when your code is converted into an AST, right? So same, let's go to SQL. That will make most sense. So if you see here, I'm just showing the JSON representation as it will make most sense because this is, I think, too cryptic. So, and it also doesn't give a visual tree. So yeah, so in the JSON, if you see, you have this from node, right? You have this where node, you have the order node, all looks like they're at the same level, right? All of them look like they're at the same level and they have a left and a right child. So where has a left child and a right child. Okay, I'll just increase the font maybe a little bit. So if you see here, where has what? Left child, right child has this, text neat, and left child has this identifier column foo. Okay, and so this is a tree representation of your SQL, right? So what we are aiming is to write these select and from. What are the keywords of my common language with which I'll play around, which I'll write queries, right? What are these keywords in my common language? So for SQL, these are the keywords. Now for our project, okay, these are the keywords. So think of this should be present like a select, one of maybe like a from, something like that. So we are trying to build an AST out of this later. But first we have to give the most basic nodes based on which operations will be performed. Okay, so that's how you can think visually in your head. So, okay, we have done this. We have now defined some kind of language. Okay, now what we're going to do is there's a little trick here that we want to show. So there's this data structure called free, which kind of helps you do these operations. Now you've written a language, but it doesn't make any sense if it doesn't do the work that you want it to do, right? So how to make it do without writing a lot of code? The answer to that is the free data structure. Free data structure is a recursive data structure which holds all your programs that you have in the correct tree structure. Okay, so if you see here how to think about this free, so there are two forms of free. Okay, I'll come to that at the end. There is a free monad and then there is a free applicative. For data expectation, we used free applicative, but for data IO, we used free monad. Okay, so free applicative, what it embodies. So if you just forget this applicative part, if you just strike out this applicative part, if you just focus on the free part here, what this says is how you can think of this. Okay, so I'm just trying to give you the base intuition and then you guys can go back and read. So the base intuition is that you have a DSL, and what would you want to do using the DSL? What do you want to do using the SQL? You want some machine, some server, some execution engine process to evaluate that DSL and give you back an answer, right? So you can think of free as the program which evaluates the DSL. So your DSL always comes in this place. Your free always comes at this place. You can think of free as the program that evaluates this DSL and gives you back an A. That's how you should think about it. A program that evaluates my DSL and gives me back an A, right? So in the case of data expectation, a program that evaluates my data expectations and gives me back an expectation result. And in case of, say, data IO, a program that evaluates my definition, DSL, whatever DSL we have written there, and gives me back a data frame, right? It will go through it and give you back a data frame, okay? So that's how the base intuition is. And if you see this free structure, there is a thing here that we have to do, which is basically lifting into a free. So basically, in order for free to hold your program, to work with it, it just can't immediately start working with it until and unless you have taken your DSL and set it inside free, right? There has to be some operation there. Let's think that, let's say for now it works, it just works, okay? So you just take your data structure. So these are all convenience methods which you have seen. These are, like I have written here, let's make it business friendly. So users who are using your methods don't know so much of free and stuff, right? They would always want a simple method where they can pass whatever needs to be passed. So look at this guy, should have one of. This is something is user friendly. Should have one of what? A list. Give me a list of string, male, female. I'll check whether your data only has male, female or not. So this is the user part, user's visible part, but they will just look into this and they will say, hey, okay, I just need to call this method, give it a list of string, male, female, and they will check it for me. Okay, the code will do that internal. And internally, we are again using the same DSL, the one-off DSL that we wrote here, right? This one-off DSL that we wrote here, but we are doing some kind of a trick here, okay, to lift this guy into a free. Let's say it is the free is the data structure which does the magic of creating the DSL. All I have to do is I have to set my data structures or my DSL into the free container. Think of it that way. I took my DSL, set it into the free container. That's it. Okay, that's the only trick that we have to perform. So free applicative also has a lift and free monads also have a lift. Okay. So having said that, now see, we have started writing rules based on my language. Okay. What is this language? The language is, so there is we are talking about some mandatory column check. Okay. What is this mandatory column check? It's saying column should be present. Okay, you have a data set, say suppose I don't know what that data set is. Again, not talking about any implementation here. Some data, their column should be present. Okay, great. Should have one of, okay, the column should have one of these entries and should always be non-null, right? We wrote this, okay. Now, the good part there is, see, we are talking in terms of business language. We have applied these three rules. And now this is a special structure on which is available on an applicative. Okay. So because you remember we used a free applicative, this method is available on an applicative, map n. So what you can think of it this way. So if I have to explain this map n here, just think the intuition is this. This guy, column should be present, has some implementation somewhere. This guy gets evaluated independently. This guy gets evaluated independently. This guy gets evaluated independently. Now you remember what these guys will return, right? What these guys will return is this Boolean, right? We have already spoken about in our DSL. We have taken this DSL, we have evaluated this to a Boolean, okay? So I can safely assume, just on first principles, that column should be present will return me a Boolean, should have one of will return me a Boolean, should always be non-null should return me a Boolean, right? All I need to tell to build a higher level rule on top of it, to build a business logic. This is a business logic, right? This is a, maybe I'm calling this mandatory column check, that mandatory columns should have these rules which will apply. IABs will have these rules. Column should be present and always non-null and maybe comma separated, something like that, right? These are the higher level rules that I'm building on lower level foundations, right? All I need to say is what to do with the final answer. So this has a Boolean, this has a Boolean, and this has a Boolean. I'm saying give the result as a AND operation. Means if all are true, then only the expectation gets passed. Okay, so I've successfully been able to take the business language and write a rule based on it. Okay. Okay. So one very important point to note here, nowhere till now we have written, look at this guy, we have written a rule, we have written a DSL, we've done some magic here, probably some containerization and stuff. We've written higher level business rules based on it. Till now we haven't even spoken about one platform or implementation level detail. Okay, now we are getting into the implementation. So this is totally abstracted out. So one part that till now which I showed can be considered as the domain. This is the domain language, domain specific language that we are talking about. Next, we get into the implementation or the platform part of it. Okay, so again, there is another thing to be understood here. There's this thing that we are doing, which is a function K. Okay, so a function K is basically what translates my data expectation to a Spark data evaluator. Now, what is this? What is a Spark data evaluator? If you look at this definition, Spark data evaluator is something which takes a data frame and returns me an A. That's it. You give it a data frame, it will return you back an A. Okay, so somehow, now one thing to notice here, see, Spark data evaluator has a A, and the data expectation also has a A. Data expectation takes this is a type construct. I'll come to that later at the end. But just to notice here, data expectation has a A, and Spark data evaluator also has a A, something which needs to be filled, a hole probably inside this data structure, right? And if you see, this function K takes these two containers somehow. It has an apply method. You have to implement this apply method. What is the apply method? The apply method is saying that I'll take a data expectation and I'll return a Spark data evaluator of A. If you say A being the constant, now if I have to hypothesize, probably A being the constant here, I'm changing the form of the container. A is the constant thing here, right? Both of them are returning, both of them have a A, some hole in them. But can I not say that I'm just changing the outside wrapper, the container? And this is probably the intuition behind how we evaluate our DSL. So you had a should be present, or you had a non-null always, that was evaluated and that returned the Boolean. Here you promised that I will return a Boolean. This is where the implementation lies. You actually gave an implementation which returned a Boolean. But what are we really doing at a high level? We are really evaluating this common language which we have defined here. A common language was defined here with no implementation as such. And now somewhere else, some weird method called, or weird class called function K, we are defining, where we are actually defining what to do, which is very much like the interpreter pattern or the interpreter itself, right? Where you're saying that what does this common language mean when I have to evaluate it to a platform? So you can think of it that way. What does this common language mean when I have to print something? So it can be, say, a printer of A. So then we'll do a printer of unit, probably it will return or something. Okay, so that's what the intuition is, that what does my common language mean when I will target it to different platforms? And the targeting to different platforms is basically implementing this function K. where you interchange or give the definition of how one container or how one wrapper is converted into the other wrapper, A being A remaining constant. Okay, so it will make more sense when I show you how to invoke this now. Okay, we have implemented this, the platform, how to work with Spark now. So you see every piece of code is separate. The language part is separate. Data frame part is again separate. And how we bring them together is this guy. Look at this. We have a mandatory column check, right? If you remember, the mandatory column check here was taking a list of string and everything else was more or less kind of fixed, that it has the column name itself, which it needs to verify and should always be null, is just like taking a column and checking if it's null or not. Okay. So it takes a list of some country probably, and see it calls some method called fold map. Okay. And it passes the interpreter separately. So the general form is, this is your program, this is your DSL. You call a fold map and you pass the interpreter separately. General form is, this is the domain and this is the platform. Platform can be changed at runtime. You don't want this interpreter, you have written, this is a Spark interpreter. You have written some other BigQuery interpreter or ScyllaDB interpreter. DSL doesn't change. DSL is still the same. You passed in a separate interpreter there, right? Does this make sense, guys? Okay. So that's the base intuition there. Okay. Take the say program or the DSL or the business language. Tomorrow the business language doesn't change, and we have, in fact, we didn't get the opportunity to reuse it in data IO, data expectation, but we have done that reusing part in data IO. I'll show that. Okay. So this is one part of it. So this is just the intuition behind free monads. Okay. So I'll switch back. I know it might be a little too heavy, but now you can see what we mean probably. Guys, any questions till now? Any doubts, questions till now?
So Joy, in the translation,
Yes.
that interpretation is happening, right? Spark data evaluator.
Yes.
So
Yes.
what are the protections in the framework? Say I write another, say, data flow interpreter tomorrow. Okay.
Yes.
So if I have to test the rightness of that, how is it found here?
So here what we'll do is, so like hello.
Yes,
am I audible? Okay. So what we can do then, say suppose we are writing something for Beam, Apache Beam, okay, which is the data flow. So what we can do is, Apache Beam will have a construct, right? P collection, which is for Apache Beam.
Collection.
So what we'll do is, we'll evaluate the P collection to an A. So it will be a Beam data evaluator, which will take a P collection and will give me back a Boolean that whether this check has passed or not. It will be as simple as writing another interpreter. My business language remaining same, I can easily port data expectation to Apache Beam. And there we'll write the code based on the P collection here. And everything remains the same. Just one interpreter we have to write. And we are done. Does that answer your question, Sadish?
Yeah, kind of. I'm just trying to figure out how are you protecting the, I would say, see, now your return signatures are Boolean in this example, right?
Right.
Okay, compile time will take care of that. Yeah, I think it will work. It's fine.
Okay, so we'll tell you how we have even worked with this in the case of our data IO. We have even experimented. So earlier this Boolean was fixed, right? The Boolean would always return a Boolean, right? We cannot play around with it, but now we have to write something for source loading and source writing, sync writing. And if we have worked with Spark, we know that half of the properties that we do for reading is set on a data frame reader, and half of the properties, like say the optional columns and look back and the very recently the zeocore array, the raw timestamp, is actually operations on the data frame. So Again, if you see here, same language that I gave in the other PPT. So what we would have written, okay, we are reifying again the same thing. So we wrote something called, say, suppose we had a format type and we took a format there, a string probably for now. The return type cannot be fixed here. In the data expectation piece, the return type was fixed, Boolean. We know data expectation always evaluates to a true or a false. Here, that is not the case because half of format type is set on a reader. So my output type will be a reader, and optional columns is basically when you have the data frame, on the data frame, we add the optional columns, column this, column that, we add and we get back. So this A will be a data frame. So now what I see is I cannot, so there, if you see, I had, there, if you see, I was coupled with the Boolean or the expectation result. Okay. But here I'm not allowed to couple my result with any particular hard-coded data type, like a Boolean or a data frame reader or a data frame, because then doing a data frame reader here itself will mean we are doing a coupling with Spark, and we cannot have that. We are building a language and we cannot have the coupling with the technology, right? With the platform, right? So we cannot put a data frame reader here. Okay, hey, format type will return data frame reader, an optional column will return data frame, and then we'll mix and match and create a, say, a data frame out of it finally. So what we are saying here is this type is a generic type A. So this guy, if you see, the format will be taken and what you'll get back is an A. Same goes for optional column. A format A will be taken and a list of columns will be taken, and what you'll get back is an A. Okay. So that means tomorrow, if I have to implement for Scylla or say for Beam, Beam has a P collection, right? And maybe the reader and data frame concept doesn't exist in Beam. So everything is set on P collections, say suppose. So then we have the flexibility of returning a P collection from all of them. Here, like I have to return reader and frame, there I can return only P collection from all of them. Okay. So here again, same thing, same slides. Okay. We took something that was implicit in the code. If you would have written it in normal function thing, and then we reified that. We said that, hey, this format type is now data. Add optional columns, which was a, think about it, add optional columns is what? It's a verb. It's an operation, right? The intuition is a method is a verb. Take the verb and make it data. That's the intuition that I want to stress on. We took a verb. Adding an optional column is a verb. We took that verb, we turned it into data, some case class. And within that data, again, within that case class, you again store whatever is required to calculate A. Again, the same base intuition. Okay. So look at this now, the seal trait here. So we added something called supported features. Okay, in data IO. So data IO works basically on supported features. Supported features can be things like format type, because remember, reader and writer both have format type. So we want to just write one language and reuse it as much as possible. We don't want to write separate language for reader and separate language for writer. And then in some technology, there is not really such a concept of separate reader and writer, and would just mingle out, you know, it would just be merged together. So we wanted to keep that free form here. So what we basically decided is we'll have a flat hierarchy there. Okay, so everything falls at the same supported feature level hierarchy. Okay, so there is a format type, there is a separator, add optional columns, add creation timestamp, and things like that. Now, one thing to notice here is within format type, there is an inheritance. There's a case class format type, which just defines my operation. You can think of it like the select. Now, whether you're writing select star or whether you're writing select, after that you have given 4 column names, A, B, C, D. Okay, that is not represented by 2 different nodes, right? There is not, if there is a node for select, there wouldn't be one node for select all and one node for select columns, where you have a list of column names, right? There is just one node select, and within that there will be inheritance. So that's the same thing in format type. One node for format type, and within that there is an enum format type, which is, you know, kind of a vaguely, if we have to put it, that there will be internal code which will kind of detect what format type and fire that code internally. Okay, so this is the base construct. You can now relate much better because of the previous module which I have shown. So again, same thing, format type extends supported features of A, separator extends supported feature of A. So what we are saying is these are the supported features. that our data IO or data source supports. All of these will be available to you. Okay. Next, same, absolutely same thing. This time, if you see, one change is we're not using a free applicative. Okay. We are using a free. All right. So we took the supported features, we lifted it into a free. That's the term that we might want to use now that we are seeing it twice or second time. We're lifting whatever DSL we have written into a free. Okay. Taking the DSL, lift it into the free so that you get a free data structure, which is doing something with our DSL. Okay. Again, same thing, taking the separator, putting it into a free. Look at, this is a little, I would say, not as simple to look at, but if you just go through the type system, if you just go through the construct, you'll see what it means. So what I'm saying is I'm getting a sequence of supported features. So now let's think generically about loading a source. What do? When you load a source, when you write those spark.read something, what you're doing is basically choosing from a menu, right? You say spark.read.parquet, or CSV is the best thing, CSV. And on that, you put an option saying, line separator is comma, field separator is colon, and first row is header. So infer header true. So what you're doing is you have a menu and you're choosing from that menu, right? So similar fashion, that means end of the day, when you have chosen, internally Spark will also keep a list of these menus, what you have chosen. Based on that, it will fire some code, right? Same here. Say suppose somebody has chosen this menu. Okay, now we are not going to the external interface. The external interface or the facade is where you choose the menu. Once you have chosen the menu, it comes to us like a sequence of supported features. So supported features were all of this. You have chosen from that menu that, mujhe format Avro chahiye. I need optional columns. I need a separator. Say, okay, format is CSV, separator is comma. And I need optional columns. I need creation timestamp also, this guy. All 4 options and many more will be there. You've chosen based on your requirement. So now all we need to do is work with these, okay, and give you the final result, which is a data frame. Okay. So what we have done is here, if you see, we have taken this sequence, reduced it, and the reduce operation is between A and B. The A and B looks like it's a monad because there is a for expression that we are working with. Okay. So A and B, we are doing something there. Okay. We are working with A and B, and we are saying that it will yield a V2. Let's take it on face value for now. We'll come to that in the next slide or 1-2 slides after this. Okay. Just remember this structure probably. Okay. So again, very important to understand, till now, no talking about Spark. Okay. Whatever I've spoken is out of my free will, but in the business language, there is nothing that we're talking about Spark. I've drawn parallels, but there's nothing about Spark here really. Okay. So now we are giving the implementation. So for the implementation, now we're using 2 monads here, reader monad and state monad. Okay. So if you are not familiar, go check out these docs. I know that it might be too much for one session, but yeah, go check out these docs. I'll just give you a very base intuition, which will be like, you can just think this is it. Okay. So we're using this cats library, the data types within this cats library. One of the data type is reader. One of the data type is state. Reader is used for dependency injection. State is used for state management. Why state management? Comes from the argument that there cannot be any mutation. It has to be immutable data structures. So how do you do mutation in a pure function? Use state management, use state monad. Okay. So what is the base intuition? In 2 lines, that's it. You shouldn't think anything apart from this. Go back, read later, but right now, whatever intuition I'll say should suffice. Okay. If not, ask your questions right now. I'll clear it out. Okay. So think of reader in a way that what is dependency injection? You get an environment. People who have done the session with Amit the last day, the interns also, you guys also know dependency injection now, right? You get an environment from somewhere, and based on that environment, you return some A. That's it. That's what dependency injection is, right? Probably this is a global environment set somewhere globally and can be accessed everywhere where annotations are, probably those annotations or those dependency injection is done, right? Many frameworks for them, Juice, blah, blah, many frameworks for them. But in case of functional, what we use is the reader monad, which basically says that I'm taking an environment, people who are aware, taking a Spark session, right? On the Spark session, we have everything, right, guys? We have the data path, we have all the small magic strings that are set on the Spark session. And what we want to return is probably a data frame, or we want to return some broadcast value or things like that, right? So this is a reader, that's it. It's very similar to a function which takes an A and returns a B, okay? That's one. And reader is, additionally, it can do some IO, okay? Because you're reading some data frame, right? It might be doing some IO. Second thing is state. So state is little trickier, but is also very, intuitive to understand that way. So what if I tell you, you cannot mutate something, okay? And I tell you now you have to work with a construct where there is mutation involved. I tell you, no, I am tying up your hands. You cannot mutate. You cannot use anywhere where you're setting or updating things. Not possible. You can only work with pure structures, immutable structures. What would you do? Okay, so you would take an S and you would calculate. So that's how the state monad manages it. It takes a S and it returns you back an S dash and a A. A is some answer. Say you use the S, which is some variable. Okay, so you say, suppose, let's take a very simple example. You got a int, okay, and you returned, say, in A, you returned the next int, okay, or you return, say, a true, which is like, this passed, this thing passed, and S dash is the new value of S. So maybe you have to return the next int, you do a +1. Okay. Earlier in mutation or mutable code, you would add +1 to the existing state, to the existing variable, and return that. Here, you would actually write some code which would add +1 to the state and just return that state. Think of it like a pipe operator in a Unix or in a Linux, what we write, right? Cat, some file. When you do a pipe, only that file's contents go into it. Then you do a grep and you say, suppose grep on error. So only that is available in error goes into, say, after that you're doing a line count, okay, WC-L. So in every stage, you're not doing any mutation. The result of the previous stage is being passed to the second stage. The result of the second stage is being passed to the next stage, okay? So this is what a state monad is. That's it, all right? And both can be used in a for comprehension. For comprehension, I'll not go into that now. It's basically, but it is very important because that is what is helping us do all of this work out of the box, okay? So you can refer to one of our knowledge transfer page videos on monads, how the for comprehension works. It's given with a demo. Basically, you can, if you just check out the talk from the last, from mid, if you check, you'll find that demo. So the intuition will be there, okay? So having said this, that these two data structures is what we are using, this is the code that we have used for the interpreter, okay? If you look at this code, if you see here, we have a reader, okay, which takes a data frame reader and gives back an A. Let's just, I think we'll not go into much detail into other slides today, but let's just concentrate on this to build the base intuition. There is a reader. What is a reader? Okay, let's go back. Reader is something which takes an environment and gives me back an A. Okay, let's take it on face value. So reader, then according to what I said here, reader bracket env comma A. According to that, okay, 1 second. According to that, this is the environment, right? This environment is this environment. And it will return me back an A. Okay, great. It will return me back an A. Recalling from our data expectation, what I explained just now, again, I write a function K, which somehow takes a feature or takes a DSL, my DSL. If you see, it has a hole which is filled by A, and it is changing my DSL to a Spark reader. What is Spark reader? Spark reader in itself Spark reader in itself is a dependency injected object, which takes a reader, returns back an A. Okay. Question is, how will we use it? Let's park that question for now. Okay. So how have we written? Just try to look at the construct here. You've taken this reader. So how do you wrap your code in reader? You just write reader bracket. Okay. So these are two separate readers, guys, just to clarify. This is a cats reader, the library that we have been talking about, this library, cats. Okay. This is a cats reader, which provides the facility of dependency injection. And this is the data frame reader from Spark. Okay, because now we are writing platform implementation. So it takes this supported features and converts it into a Spark reader. Okay, keeping the A constant. What is this A? We don't know. We'll come to that. But point is, keeping the A constant, it converts my DSL into a Spark reader. What is that Spark reader? It takes a data frame and returns me an A. Okay, so now let's see what this guy is doing. So what we have done is we have just encapsulated this into a reader. So once you do a reader, okay, this is a basic syntax of a reader, that once you write this, what you get here is a data frame reader. Okay, because remember, it takes a env, gives back an A. You're writing this code as if you get a reader, what would you do with it? Okay, so this is what it means. You got a reader, and internally you'll write some code which tell you what to do with that reader. If you get a Spark session, internally you'll write some code which will tell you what to do with that Spark session, right? So here you got that reader, you can directly write it, because there is a reason why you can write this code. Okay, the reason is you have defined this return type for this function. What is the return type? Spark reader. Because you have a Spark reader here, you are able to write a code which can take a data frame reader. It is evaluated, it is compiled in IntelliJ because of this, because you've given this return type. So now you have a reader. All you need to do is just write some code on the reader. You have a reader, you got format type. Oh, format type, you say Avro. Cool. You just went here, you just set it to Avro. Then you saw separator. Okay, separator is comma. Now you know this is your plain old Spark code. Reader option, set the separator, right? So you keep writing this. Now question is, why did we take the pain of putting these things into a reader? Okay. So anyways, this reader takes a reader, returns back a reader as well, right? What is the pain of can't we just have given a function which takes a reader, returns back a reader, right? We could have done that also. That this, instead of being a reader, could be a data frame. So what I mean is, here it could have been a data. So let me know if you follow along. This looks very much like a function, right? Data frame reader to A, something which takes a data frame reader, gives me back an A. In this case, that A is also a data frame reader. Couldn't we have just written this? Why use this overtly complex data structure called reader, which does pretty much the same thing, takes a data frame reader, gives me back a data frame reader? Why such a complex structure? And this is where the explanation of this guy comes into picture. This features compiler, which we have in the previous slide, remember? So if you see here, we've written some code. I said that this in reader, I have said this works well in a for comprehension. And I've written a for here where I've taken two A's. Now remember, what are these two A's? These two A's are the readers. When I have a supported feature which will return me an A, remember, supported features returning an A, right? In this case, A itself, this entire piece itself, I'm evaluating my supported features to a Spark reader. So this returns me a reader, right? And now when I go back, what I have written here is it might look like just two lines of code, A and B. That's it, A and B. And looks like I've not even taken this, what this guy is returning, and I've taken this and I've returned this, something like that. It looks like, okay. But in this two lines of code, what is happening is, it is the by default behavior of reader. When you put two readers in a for comprehension, it passes the environment as it is between them. You don't have to. So okay, let's for argument's sake, let's say this is a reader. Okay, great. This is a reader. What this reader does is this reader takes a reader, okay, and returns me back a reader. Great. Took a reader, returned me back a reader. If you see, then I should have taken that reader here and passed it to the next reader, but that is not required. That is the behavior of reader, that whatever environment you are putting inside a reader, whatever environment, this is the environment. Remember from here, this is the environment. Whatever environment you're putting inside a reader, reader will do the passing around. And that is why it is dependency injection. The dependency is being injected by the reader. Okay. And this is where it happens. So we are not even capturing the result here. We just taken the result and just called these two. Automatically, whatever comes out, the data frame reader will be passed in the data frame next reader, which we have already defined. Okay. Guys, any questions till now? I don't think we have enough time today. We have a small part, but you can look into this PPT also if it made sense. We had one part which would basically show the same thing, why we used a state monad, what was the problem there, how to invoke is already something you know, and probably some intuition behind function key and this thing, and maybe we'll cover this in a next session. Okay, so yeah, any questions till now, guys? Connect, anything?
So, Joy, any application that we are using this library in, maybe you have already presented, but
yes. So how the usage is basically, we are not asking the user to have a very bulky kind of, usage. The usage is based on these Spark loaders that we have. Okay. So the usage is not like they will have to call the DSL. They will be using very simple to use loaders on top of it. Okay. Maybe I'll show that part. 1 second.
yeah. So my query was more of like if we have used anywhere, and maybe I'm missing that presentation, but
yes.
If you can give that link, GitHub link, maybe we'll try to use it in Connect repos house as well.
Yes, makes sense. We can do that. And we'll take a follow-up session on the usage, because this is too large a topic to cover in one session. Maybe we'll go over a follow-up session. Does that work?
Yeah, yes, that is needed.
Okay.
Yeah.
We'll show the usage actually, where we have used, how we have used, everything is there, but it's just like it's too big a topic basically. So yeah. So I'll stop the recording. I think you all have other meetings to go to. Can anybody stop the recording? I'm unable to access.